Welcome, everyone. Thank you for attending today's webinar about preventing PT failures and locating generation loss with Synchrowave operations. My name is Tristan Beaudois. I'm a marketing program manager from Pullman, Washington, and I'll be today's moderator. Before we start, though, I'd like to bring a few items to your attention. This webinar will be an hour long, including questions at the end of the presentation, and there will be a recording available on our website shortly after. During the webinar, all participants are muted, but if you have any questions, you can submit them in writing using the Q&A tool at the bottom right-hand corner of the application. Our panelists will respond in writing throughout the presentation, and the presenter will also answer questions aloud near the end of the webinar. Any questions that aren't addressed during the live event today will be answered afterwards via email. Today, we have Development Lead Engineer Josh Wold joining us to help answer questions and lead the live Q&A, and our presenter is Jared Bestbrewer. Jared is the lead product manager for Synchrowave software at SEL, where he has over 10 years of experience working with time series power system data. Jared earned his bachelor's degree in electrical engineering from Washington State University and has supported over 100 deployments of streaming data visualization for power systems around the world. Now I'll pass the microphone to Jared and we can get started.
Well, welcome everyone. Thank you so much for the opportunity to share with you some of the work our team's been doing. Today, I'm going to cover two new features that we've added to our Synchrowave software, specifically in identifying and preventing PT failures with using this data, and also some work we've done with generation loss detection. Before we go too much further into that, though, I'm going to give you a little bit of an overview for those that may be new to Synchrowave software and what we've done. So Synchrowave is really our analysis and visualization software at SEL, and we focus on taking all of the data that the devices that we build generate, and then provide that information to engineers for event analysis or operators for visualization. And we've recently released a new generation of Synchrowave, and one of the products built on that platform is called Synchrowave Operations. And the intention of this software is really to start to bring together many of the different sources that are available of information together into a holistic picture to give you that insight that's now needed as we've gotten to this point in the grid. And I'll talk a little bit more about that as we go through the course of the presentation. I'm going to spend a couple of minutes here covering a few additional overview items, then we're going to go into a short demonstration, and then we'll go into each of the details of the specific topics of today's webinar. So from a high-level perspective, what's driving the need for us to look at higher rate time series data? And a lot of that is coming from the dynamics of the power system changing, and that's, of course, due to a lot of the inverter-based resources that are being added to the system. And one of the challenges with these inverter-based resources is that these dynamics that they generate occasionally, whether it's a forced oscillation or many of the other characteristics, simply happen at a rate faster than SCADA, our traditional measurement approach, can really detect and understand. And so here you can see on this slide we have information where you can see an oscillation from a wind farm from the United States from a couple of years back, and you can see that there's this growing oscillation, which ultimately results in that generation source tripping offline. And what you can see by looking at the SCADA data on the same screen is that really that data provides limited visibility, and by looking at it, I can't really understand why that generation source potentially was removed from the system. And so that's the type of visibility that we're talking about that's going to help us as we transition as an industry into a system where we have a significant amount of this renewable generation and inverter-based resources contributing to our system. And then as we've worked with partners over the last 10, 15 years deploying some of this technology, and as we started to think about what does the next generation software platform work look like that utilizes this information, well, we began to realize that, and many of the utility partners that we worked with brought this to our attention as well, is that as these systems grow, we run into new challenges given this higher data rate. We're dealing with a lot of data. So nobody wants to sit there and just look at this time series data on a trend all the time. We need to help provide and bring this information to the end users. And so we have a big data problem here, and it's really an opportunity for us to look at some new methods to bring this data together, and I'll share some of those during my demonstration quickly. The approach that we've chosen to take, though, is to have this time series data and then run analytical applications, whether it's in real time or historical, run applications on the data to mine the data or detect in real time events that it might be of interest. And instead of focusing on an individual event from a singular location, we're really looking to describe system conditions. So can we tell you that all of this data points to a generation trip in this location, or all of this data points to a PT failure at this particular location? And so that's really the intention behind utilizing and leveraging high resolution data that's now available to us. So at this point, I'm going to go ahead and transition over into a demonstration, and then we'll jump back into specifically looking at an operations use case and an engineering use case for this data. But before we do that, I want to give you a picture of how this data is used or how you interact with it. And as you can see here on the screen, what you have is in the orange section, you've got your synchrophasers, your event reports, and what we're calling streaming time domain data or continuous point on wave. This data is coming into what we're calling our Synchrowave platform, and Synchrowave operations is the operator or the engineer user interface for accessing that data across these servers. But really, it's there to complement your existing SCADA, your EMS systems, and other analytical tools that maybe weren't designed for this higher rate data and have a different set of use cases. And so I'm going to go ahead and switch over now and give you an outline of that application. So what you're going to see here is we've got a web client application here, and I'm going to go ahead and jump back into real time here for us. And what you'll see here is the first aspect of interaction with the software is really this timeline along the top. And I like to think of this timeline as essentially like a DVR, and what we see is for our TV. And it's the ability for us to go back to any point in time and see the system state, also replay from that point in time in the system. So here you can see I'm in real-time mode here. We have this range here, which is showing you what data I'm looking at in the system. And I can just go back to any point in time, and I can see what data is at that point in time in the system. All of these displays are synchronized to this point. So if I go click over here, you can see, you can also zoom out and get a larger picture instead of looking at 10 minutes. Maybe I want to look at an hour's trend, for example, and we'll talk a little bit about some of that capability as we go out through the presentation. But one of the key aspects for time series data is really that need to be able to navigate through it quickly, efficiently, and we really want to make it as seamless as possible for you to move from data that's coming into the system now to data that we saw a week ago or 20 minutes ago. So underneath the timeline within the application, what you're going to see is we've got this concept of dashboards, and this is the primary mechanism in which we communicate information within the software. You'll notice that dashboard-based software has become increasingly popular over the last maybe 5 to 10 years. And that's really as a result of you being able to bring multiple pieces of information together while keeping them independent, but also giving you the ability to synchronize and tell a story through them. And so on this dashboard, what you're going to see is we're looking at systems. So we're looking at across multiple assets. And so here you can see we're looking at like an overview dashboard where I might have a geospatial display. I might include weather information, lightning information overlaid on top of my physical assets here. And then I might have other information supporting that as well. I'm going to go ahead and show you a couple of other system level examples that utilities might use or industrials might use to gain visibility across their system. And then we'll talk about a couple of the other different modes. Maybe one of the first examples and use cases for this time series synchronized data was phase angle information representation. And that was driven from several blackout events that we had in the United States over maybe the last 50 years. And those particular events led to a need in visibility of phase angle across transmission corridors, across points of interconnection. And so what you can see here, for example, is we might have a phaser scope showing the stress across my system, or I might be monitoring a point of interconnection with here, for whether that's for like a microgrid or an industrial facility. I might be interested in that. And then over to the right, maybe from more of a utility perspective, I'm displaying the phase angles across core transmission lines within the system, so I can have that visibility at any point in time and know if there's any phase angles that are exceeding particular limits, for example. I'm going to show you a couple of other different use cases from the system level as well. One of those is maybe voltage monitoring and doing that voltage monitoring geospatially. So here on the map, we have a contour that's showing you, pockets of higher voltage or maybe lower voltage in particular areas of the system. You can also see that information, for example, in a bar chart along the left where we're showing your lower limits and your upper limits on the right, and the ability that you have to drill into any one of those particular locations or several of those locations and compare those measurements across the system and see the impact. So whether it's power flow or voltage, phase angle information, and others, we're looking across the system of assets, and we want to provide that, summary key performance indicator type information here for you. The next step, though, is really for you to be able to drill in. So when there is an issue, maybe in your SCADA system, there's an alarm, an operator can't quite figure out what's impacting the system, there might be a need to drill into the higher resolution data. Or you're an engineer supporting like post-event analysis, maybe there's a fault on the system and there's a need for better understanding of what happened. And so in both of those cases, what we want to be able to do is, as a user, drill in very quickly to a particular asset and see all of that information. And so what we're going to go ahead and do here is you're going to see, we're going to zoom in on the map, and we're going to go ahead and select by holding control and clicking on that location. And what that did is it zoomed me into that particular asset. And what you'll notice here is that instead of looking at this dashboard or system level dashboards, we're now looking at this term, the section of the software called assets. And so here we're focused on that high resolution information or bringing the information together for these individual locations. And those locations could be a transmission line, it could be a distribution feeder, a microgrid, a generation site. We can define those assets as needed. But what it gives you the ability to do then is see specific information from that. So you can see, for example, if I go over to phase currents here, there's a dashboard that's already configured. So as an engineer or an operator, I know when I click on that asset, I'm going to be able to go look at the phase currents, the live values, and look at the historical data. And this could be helpful, for example, if there is a line operation and I want to make a reclose decision, I'd like to see the current waveforms, for example, or if when there is a reclose operation, maybe there's a failure of that reclose, I can see and verify visually that one of the phases didn't close in time, for example. And so you can look back and scan and see what the performance of that system has been, like the current across these lines. You can do that same thing for example, for power. So I can go look at what's the last 1 hour data power on this particular one. One of the things that we've been doing is really, as our industry's been moving towards like dynamic line ratings and limits of that nature, we've wanted to incorporate the ability for you to take that stuff into account and make that visible to operators as well. So here you'll see just kind of an example. It's a fun example in where we actually created a sine wave as a limit. So it's like using a signal as its limits here for the power. And just as an example of being able to support those dynamic limits and then go back in time and see what the limit was with respect to the actual signal. Those are all stored in the historian as well. So that's just a couple of examples of how you can drill into a specific asset, see that information, and then have that ability to navigate through the data. The last example that I want to share with you is, it goes back to detecting events within the system, and as we get more and more data, how do we bring those and surface those to the end user? And so one of the things that you'll see here, we'll see there's a notification going off right now. You can see there was a frequency event. You can see there was an oscillatory event here that happened a few minutes ago, for example. And you'll see those indications of those events are also brought onto the timeline as a user. And so I can go ahead and click on those events, and what it will do is it'll actually bring me as a user into the software and to that, it'll kind of curate the display for me. So here you can see I clicked on this frequency event. Here you can see it gives you a primary location, and then it indicates that there were 17 other locations that detected this particular event. And you can see that geospatially on the map where all the locations are highlighted that were involved in the particular event. And when we look over at the system response off to the right, you can see that makes sense, because what we have here on the system response, we have a generation signature. And what you'll see is by using that high resolution time series data, we're really able to reduce the burden in terms of alarms and events that the operator or the engineer get. Because when we look at this threshold that was crossed, we can see all these signals cross this threshold at basically the same time, which makes sense given that this was a frequency event here. And we can group all of those locations into a singular event. So now, when I go ahead and I drop my cursor here pre-event, you can see the topology of the system down here in the lower left. And then when I go post-event, I can move my cursor over here. Since it's got that time series historian for me, I can see the state of the topology of the system also change as respect. So here in this particular event, it happened about 5 years ago or so on the Western Interconnection when BC Hydro disconnected from the Western Interconnection. And so BC Hydro is connected to the Western Interconnection through a set of lines. And this is just a single line representing that set of lines. But when that disconnection occurs, to all these measurements that we have in the Western Interconnection, that looks like a large generation source dropped off the system, even though it was just a line operation. Now, if you were to get measurements from the BC Hydro system, you would see the frequency spike up like it lost a whole significant amount of load from the Western Interconnection. So this set of line operations. So then what we wanted to do is say if there was this set of line operations, we want to be able to correlate the relay data. And while I don't have it set up specifically on this demonstration, we do have software that automatically collects event records from SEL relays and others and can store that information in a database. And then that information, those event records, can be correlated with this streaming data. And so you can drill in and see the oscillography there as well. So that's really the big level, high-level picture that I wanted to share with you in terms of the ability for you to see the system as a whole, drill into a specific asset and find more information, and then also have these events kind of curated for you. Lastly, I'll just mention that all of these displays are configurable. We have a whole set of panels that you can use. That's what we call these individual components. They all can be drag and drop, and you can build dashboards that are custom to your use cases. So while I showed you maybe a transmission example, set of transmissions examples today, we have utilities that are working in industrial spaces, industrial spaces. We have utilities that are smaller and larger, and they're all working in this, the same concepts that I talked about: system, asset, and then notification of events. So at this point, we'll take a couple of questions on this bar. If you have any, please stop in. I'll be able to come back to the demo hopefully at the end of the presentation. But what I want to do now is go back to the presentation and share with you a couple of examples from partners that we're working with and how they're using it and what some of the capability we added into the software to help work with them. So I mentioned that the software is, designed for use in grid operations, but also has engineering use cases as well. And we did a presentation with San Diego Gas and Electric back in 2020 at a North American Synchrowave Initiative, or NASTY meeting, which is basically a conference that looks at time series data and how we can help use that in the utility or the power system space. And some of the things about SDG&E is they're looking for situational awareness, advanced notifications, geospatial integration with weathers, and oscillation detection. So you can learn more about this presentation. It's posted on their website. but I'm going to share with you a couple of the different things that we've done recently and one of the new features that we added to help support this. So I just showed you an event with a generation loss, and we're going to go back to that topic for the next part of the presentation. So here you can see is that general signature of a generation loss. And one of the unique things about looking at these generation loss events, especially when you're looking at the frequency, is it's very difficult, I would say almost impossible, for you to tell the location of this event by just looking at the signature, mainly, right, because that frequency response is tracked throughout the entire system. And so if we look at maybe a traditional video wall installation where an operator might be looking at a video wall and seeing information within their system, maybe they're looking at frequency and voltage information. If there is a generation loss event on here, one of the first questions they're going to ask is, hey, what is that? Where was the location? And so if you look on this screen, while it might not be a generation loss event, you can see that there are spikes in particular events that are happening on the system. And it's natural for us to start to ask, what is this? What was this? What's this? And so that's one of the things that we set out to solve, is how do we give a display to a grid operator with minimal interaction on their part, but start to provide them information about what we're seeing in this higher resolution data that can help them make better decisions and be more informed. And so one of the things we decided was to go ahead and start this process of detecting and displaying information, but we're going to start it with generation loss events because there's a couple of different challenges that make them unique, but also makes them beneficial to doing this. And so these generation loss events I already mentioned, they're difficult to detect by just looking at data. And when I mean detect, I mean the location. It's very easy to determine that it's a generation loss event, but it's hard to tell where. They are also significant system events, and they often impact the operation. We might have to take actions based on them, so they have value in that sense. And at least in the Western interconnection, I'd suggest that these generation loss events are relatively common. And they're going to be seen by a lot of utilities within the system, even if the event wasn't maybe within their region. So we did some research and we tracked 20 generation loss in events that were of significant size in a 2-week period of time last year. And so what we wanted to do was then give the operator, you saw the display, we want to give the operator a way to see that information and then get that information immediately without having to interact. And so one of the things that we wanted to do was provide an overlay over the particular event and then give them information, as much information that we could determine by processing the waveform. And so we could give them information such as maybe out of system generation loss event, closest substation is X, and that's valuable for a couple of different reasons, and we'll talk about that. So how do we go about detecting these generation loss events? And there's a little bit of a challenge here, right? We'll have a threshold, for example, where maybe the signal needs to cross a particular threshold before we want to detect, and that might happen after a certain period of time within the data. And so this blue line is representing maybe the time when we would detect this frequency event. But we really, in order to detect the location, we need to go back and find the event onset. So we have to develop an algorithm that goes back in time and then processes this data. And what we're trying to do is find the location that essentially saw it first. Now, with SCADA type measurements, we wouldn't have the level of resolution necessary in order to be able to really do this. But with the time series data and synchrophasers, we have enough resolution in order for us to start to show the propagation of these events, and I'll show you that next. So once we've done this processing, we're going to go ahead and sort these signals essentially as they move down. We'll order them, as you kind of see as we zoomed in, and we'll order them by their propagation here. And this is essentially showing who saw what first. But there are some challenges in determining the location, especially when we're intermixing PMU database. Data quality can be a challenge. Different devices filter differently, and so there's some challenges there as well. And there's a couple of others here that could also impact. Well, we took the algorithm that we've developed and we went ahead and ran it across 5 different events that happened on the Western interconnection. You can see some of the information here. Of course, we do have more accurate, but this is kind of the public location information that we can share in terms of the location. and then also the algorithm results. So you can see that in each of these 5 different cases, the algorithm was able to detect the PMU and the system that was actually closest to the particular event, given the data that we had. So let's go ahead and look at some of those events and show you kind of the propagation of those events. So here we're taking PMU data again from several different locations within the Western interconnection from different utilities, and that information is brought together. And for the particular event, we then run that data through the algorithm. And what it gives us is the ability for us to kind of map out the propagation. So you can see the red, the big yellow circle is representing the closest location where we have a measurement for this particular event. Now, in each of these events, we do know the actual, source event. So we can then determine, okay, for this event, that was a coal steam generation loss in the Montana area. We can see the closest PMU we had was located over here. And we can see that by the arrows, that we're drawing the arrows showing the propagation. So by propagation, we're measuring, again, that just those waveforms that are coming through and taking the timestamp when we see that change. And so you can see how the event moves through the system, and it transitions and goes north towards Canada. It comes down, moves through the Western interconnection, and then out down here towards Mexico, and then back this direction. So you can see that that's the propagation. Now, what would that look like maybe on the display? In order to keep it a little simpler, here's the signature of the waveform for this particular event. You can see that's clearly that generation loss signature. And then we're going to have these messages that says, for example, there's a generation loss and the closest PMUs, for example, maybe in Montana, for example. And we would go into a little bit more detail than that. This is just a little bit more simplified version here, for example, in terms of the information included. Next, we had a generation loss event that happened in Northeast Washington. This was a hydro generation loss event. And you can see that event, the closest location, PMU, was located here. And you can see, again, how the propagation shows it comes down this transmission line. Then we move to the left, we move to the right, and then it comes down through the system. And you can see just how all the arrows are pointing in the direction that we expect that to flow through the system. And here you can see that generation truck event here, what that signature looks like, and then the overlay on the software display, giving the operator a sense of the location of that particular event. Here we have our third event, which is an event up in from British Columbia area. And you can see how that event propagates down, moves east and south through the system. And you can see what's really cool about these events is that even all the way down here in Southern California, you can see that the direction of the arrows is all making sense. It's all aligned. So even though we might be a few thousand miles away from the source of the event, that propagation, the electromechanical propagation of these measurements is really still lining up well. Here's an example of what that signature looked like. I'll go ahead and go to the next event here. This event, again, in Northeast Washington, here you can see the closest PMU in this particular case. And you can see, again, how it's moving to the left and south and then moving to the east. So we can kind of identify that location. And here's that waveform again. Here's another example. And then the last case, we can see there's an event in north central Washington. Again, and you can see the propagation of the event. You can see how it's moving through the system, again, to the east, to the west, and then down to the south eventually. Good. All right. And here's the last, here's the display. Okay. So that's one use case. There's a lot of different use cases. We talked about phase angle monitoring, in-grid operations. We've talked about power flow monitoring. This is just one of the new applications that we added, the generation source location application that's intended to kind of provide when you have some of the utilities within the Western interconnection are exchanging information among each other. And so while, for example, I might be a utility in San Diego, I might have access to data throughout the rest of the Western interconnection. And how can I make that data valuable to my grid operators in, for example, San Diego or Southern Cal, Edison, or SRP or APS? How can I make that data valuable to those operators? And one of the ways to do that is to give them some more context around the data that they're seeing. And so that's just one of the examples that I wanted to share with you. Next up, I want to go through a couple of engineering use cases here, and then we're going to go through an example of the PT failure detection. And I shared a little bit earlier in the demonstration about how utilities are using the information to support their fault location, their event detection efforts, and using that aspect of software. Another aspect on the engineering side is really, hey, how can I help with model validation? How can I help root cause events? And the one I'm going to talk to you today about is maybe how we can do some predictive analytics based on this data. And so that leads us to the equipment failure. And of course, this is not what we want. We want to detect before, if possible, there's any particular failures, so we can plan this maintenance in advance. And today I'm going to specifically talk about a use case, and we wrote a paper with Salt River Project on 2 failures of a PT that they had and how they used this particular data to go ahead and identify those failures and then make actionable decisions from that. So that paper is on our website, and it's available for download, and we can send you guys a link as well if you'd like, maybe in the chat. But we're going to talk a little bit about that use case and share some of the presentations we've shared at other conferences related to this. But essentially, we have this voltage transformer, and that information can be monitored essentially via like DFRs, PMUs, relays. They all support this streaming data capability. And in traditional methods, you know, that data might be sent off to SCADA, for example, or analyzed in different methods. Of course, some of the reasons we're going to want to detect these voltage transformer failures is, you know, there could be improper relay operation if it's operating based on false data, or we could send false alarms. Could be a misrepresentation of phase angle measurements. And there's several others that are listed here. And then, of course, there's personal safety and substation equipment damage that we're looking to prevent. And so there's a couple of definitely reasons for us to investigate this. So what are some of the existing detection methods? Of course, the protective relays have implemented over time loss of potential logic, which then essentially asks the relay to disable protection functions that rely upon that measurement and maybe go to some subset of protection functions. So we definitely don't want to be in that state where we're not using the full protection scheme that we have designed. And then there's also some SCADA-based protection method or detection methods for PT failures, and those are operating maybe at a little bit slower rate. And both of those methods depend on a voltage drop of a significant portion. And what you're going to see in these examples as I go on is that that may not always be the case, or at least we may be able to identify it earlier in the process and give you more time to schedule maintenance. So here, this particular method does rely on PMU or synchrophaser measurements. This is an example diagram of Salt River Project's PMU system, and where they essentially have DFRs and PMUs or relay PMUs and their substations, and those are sending data back to a centralized location. This is typically referred to as a phaser data concentrator. And from that phaser data concentrator, the data is then distributed to different environments. You might have software running in a grid operating environment, and you might have software running in an engineering environment. And then that data is then accessible by operators and engineers, for example. So this is, for example, just a couple of screen captures from their implementation of events that they've had on their system. And now we're going to jump into these 2 cases. So about a year ago, they had 2 particular cases. And the first one we're going to talk about here. So what you'll see here is that on the trend, you're looking at your A, B, and C phase voltage measurements. From a particular location, you can see we're dealing with about a 7.2 kV here on the voltage level here. And so you'll see these repetitive measurements where we're dropping, and this is on particularly on the C phase, you're going to see these drops. And these drops occurred for about 2 weeks into the system. And the screen capture that I'm showing you right here is the last voltage drops that occurred right before they took the PT out of service and began to C-phase, to service it. So here you can see they're servicing that C-phase PT. Now, in this particular case, it was just a fuse failure, so that's good news. But after replacing that fuse, they were able to return back to normal here. Now, this one is really unique because if you look at these spikes are really only about 1 to 2 samples. So you can see if we're sampling at 60 samples a second, and we've got just a couple of samples here where you can see this. And the thing to note here is that these voltage drops, these were only about between 1 to 3% each of these voltage drops. So most of our traditional methods, probably all of the traditional methods of detecting this, wouldn't actually detect this particular failure at this point in time, at least until there was significantly more degradation. And so you can see here, there's that value there. So I'm going to talk about the second example now. And so you can see the second example started to occur on 8/1. We're looking at a little bit bigger data set here. We're looking at 7 days of data. And something to keep in mind, while it looks like this voltage degradation, again, in C-phase measurements, which is the dark ones, just happens to be C-phase in both cases. This is a separate, totally separate location. You can see that by the voltage KV level on the left. What you'll see is that it looks pretty substantial, like obvious, but as you zoom in here, we'll see as these samples and drops, they're actually relatively short in duration. Again, just a few samples at 60 samples a second. And while looking at this trend, we're looking at a week's worth of data at that data rate. We're dealing with several million data points on this trend, but given that our monitors only have a couple of thousand pixels for us to work with in terms of displaying information, we have an algorithm that goes through to make sure the worst case scenario is always displayed on the screen. So you go through max min algorithm and identify that. So it really looks like this is happening very frequently in the system, and it is. So about, again, in this case and in the other case, there was an engineer within Salt River Project that was interested in this data, was investigating, ended up seeing this particular behavior just by looking at the data, and then was able to go ahead and create a service request. So they went ahead and they went and serviced the particular PT, and you can see, and that was about 5 days later from the initial discovery. And you can see that the behavior actually got worse after the servicing. And before they were actually able to send another crew back out to investigate, you can see there was a failure here on that C phase where it just dropped down to about 30%. Okay, and so shortly there, of course, after that, they go out and they replace this fuse. Again, in this case, it just happened to be a C phase fuse for their PT. After that replacement, they were able to return back to normal. So in both of these cases, whether in this last example, they had about a week notice prior to the eventual failure. And in the example before that, they had at least 2 weeks because they ended up replacing before an actual failure incurred that ended up compromising the system. But you can see in both these cases, by looking at the data over a period of time, we're able to make some decisions looking at that data that can help lead to improvements. So what we wanted to do then was, given these cases, we wanted to work with SRP, get some of this data, and then develop an algorithm to go ahead and automatically detect this. And that's the algorithm that we just recently released into the software. And I'm going to go now and hand it over to Josh Wald. He's one of the research power engineers that ended up working on the algorithm. And he's going to kind of walk you through the approach that we've taken. Again, for more information, we have a paper on our website that describes the algorithm and talks through it. More than welcome to read that, but Josh is going to go ahead and take over now. We're going to talk a little bit about the detection method.
Thanks, Jared. Can you hear me okay?
Yeah.
Okay. Yeah, so you all saw the types of signatures that we're trying to detect here, and so they're pretty unique and pretty rapid. So it's not a huge challenge to detect them. The challenge is to distinguish them from actual power system events, because you see voltage drops, in the real power system related to false and that sort of thing. Most of this algorithm I'm going to talk about is sort of distinguishing between actual power system events and these transformer failures. So the way that we do this is we start with voltage, magnitude, and angle, do some pre-processing on them, and then there's some logic to detect a failure, and then do some post-processing to sort of make sure we're not false alarming, and then ultimately produce the alarm to the operator or engineer. Next slide, please. So we take, as I said, magnitude and angle, PMU measurements. So the voltage magnitude is the top processing stream there. So we convert to per unit, do some filtering to remove samples that are sort of anomalous. So if you're familiar with PMU data, you know that you get these occasional anomalous samples, and you just want to make sure that those are not tripping this algorithm off. And then we do something similar for the angle data, except we take a derivative to sort of remove the walking nature of PMU angle data. Next slide, please. Okay, so this is just an example of some data going from raw PMU data on the left, magnitude and angle, over to process data. So notice the magnitude goes from the nominal voltage down to per unit, and you'll see a few of those, a bit of smoothing going on, and then the angle data goes to essentially frequency deviation data. Next slide, please. Okay, so this is the sort of the heart of the algorithm here. I won't go through every last step here, but you can sort of see each of those pre-processed signals, each phase of voltage, magnitude, and angle gets passed through a low-pass filter, and then there's that subtraction block. So essentially what's going on there is we're just removing the mean, so to account for the fact that the voltage on each phase can be a bit different, in normal operation. And then the middle, I guess the second sum block you see there is the sort of the primary way that we make sure that we're not picking up power system events, we're only picking up these transformer failures. And the way we do that is to do this sort of phase-to-phase calculation, so that the idea is that if we only see this on one phase, it's much more likely to be a transformer failure than if we see it on all phases at once. That would be very unlikely to be a transformer failure. So we get these phase-to-phase signals, do that both for the frequency or angle data and also for the magnitudes, and then do some more filtering, smoothing, and then do an absolute value. And ultimately, we're going to just compare the differences between those phases to a threshold. And so if we see large differences, those are going to trip off the comparators there. And then the set of AND gates on the right there are basically saying, if this is a problem with the A phase, we're going to see it in both the AB signal and the CA signal, right? Because those both depend on the A phase. And then the last is that sort of another layer of making sure that we don't trip off when we shouldn't, and so we need to see it in both angle and magnitude data to call it a problem. Okay, next slide, please. Okay, so this gives you a picture of after we've done all this processing, we go from the pre-processed signals here on the left to these signals where you see the spikes on the right there, that indicates the algorithm is saying there's a problem going on. And so you can see there's a bit of transient at the beginning there on the top right picture, but other than that, these spikes on the right hand side correspond to the locations of the sort of the rapid drops in the signal on the left. Next slide, please. I think we already talked about this, so we can skip this one. Okay, so this just shows those signals after being pre-processed that Jared showed, and you can see where it's dropping. The stars on the bottom there are indicating that the algorithm has basically detected those drops as being potentially related to a transformer failure. And then, of course, there's all kinds of stuff going on the about the 20 hour, 10-minute point because, they were taken out of service. So. Next slide, please. Okay, so then we take those spikes from the picture on the last slide and do just a bit more processing to sort of average them and aggregate them to make sure that we're not picking up on just a single sample, and then we compare to a threshold and then apply, if desired, pick up and drop out, classic pick up and drop out timers. And so once we finish all of that, then if the pickup time is exceeded and we've crossed the threshold, then we're going to send a notification or an alarm to the user to have them take a look at this data. So this is the final output of the algorithm, and so we've got the threshold set here at 1%. So this is basically saying if on average over a 60-second window or so, 1% of the samples are failing or indicating failure, then that's when the alarm would go off. So at about the 1945 point, the operator would have gotten an alarm. Okay, Jared, I think I'll let you take it back over.
Yeah, that looks great. I think we'll skip through this. I think at this point, we definitely reached the questions point in our webinar. I know there's been several questions submitted. We could take a couple of those off at this point in time and go from there. And if we don't get to your question, we'll definitely follow up via email as well.
Okay, Jared, I'll go ahead and read you the first question here. It's more of a general question about the software. Does the software monitor PMU data quality?
Good question, yeah. So PMU data quality is usually detected and the flag is set at the measurement device. So there's in the IEEE C37.118 stream, there's a data flag there for data quality. We also do some what we call, so we can take that into account within the software. Secondly, we do some calculations within the software to calculate overall availability of a particular signal. So for example, if one signal is one location is only sending in 75% or 80%, we can alarm on that and then provide that information to you to be able to go ahead and investigate why that particular device is not receiving or sending data, sending data at a higher rate. And that could be due to a variety of factors, whether it's network bandwidth or some of the different challenges that there might be.
Okay, great. Another question. What alarm features are available to alert the operators to abnormalities?
Sure, yeah, that's a good question. So, of course, there's a couple of different approaches here if I jump back over to the software. So we do have, of course, a summary up here in the top right-hand corner of the software. And so certainly the intention there is by having this summary, regardless of what display you're on, there will always be some summary information here to let you know what the current status is. We do also include those indications in the timeline, but you can see if you're looking for a more traditional alarm view, we do have a table within the software that can give you the ability to, investigate further by clicking the icon and drilling in, but also see a summary of that information here, whether there's any comments on it, whether it's been shelved, what the levels were, and the duration. So there's certainly information where we're logging this information as well. So good question, thanks.
Okay, and then I've got a couple of specific ones here, Jared, on the PT failure that maybe I can take. So the first one is, for this PT failure detector, do you need 30 or 60 messages per second, or what is the minimum rate needed? Yeah, we support 30 and 60, and then for, say in Europe, 25 and 50. But yeah, we currently do not support lower than that. And of course, it gets more challenging the lower the rate goes because you can sort of just fast-moving changes get filtered out. And then another one on the transformer failure detection. Are the evaluation window and number of samples used to declare the failed transformer alarm user settable based on lessons learned from the field? Yeah, that's a great question. And yeah, they are configurable. We made some efforts to hide some of the more complicated configuration from the user, but they definitely are. And I will say we don't have a lot of lessons learned from the field yet because this thing just hasn't been in the field very long. But we are, we're excited to work with customers to, sort of improve it as we go along here.
Yeah, just to clarify on that, at the beginning of this month, we released the PT failure algorithm. So certainly there's other utilities that have had this data for a while that could have those events in them. And as this gets rolled out to the utilities, we may see more events, and of course that'll lead to more follow-up. So good point, Josh.
Okay, a couple more here. How many of the dashboards are pre-configured or canned, or do they take quite a bit of configuration to set up?
Yeah, that's a good question. Something that we recognized very early on and through some of our previous experience and previous generations, but dashboard configuration can be burdensome, especially from a system maintenance perspective and monitoring. And so one of the things that we wanted to do was to make the dashboards the ability for you to have templates. So when I come over here to, for example, back into my assets, and where this gets becomes very valuable is when we start dealing with assets. So if I have a transmission line and I want to see that transmission line view and the dashboards associated with this transmission line, I want to see it on every single transmission line. So if we don't have dashboard templates capability, then all of a sudden you're going to get very easily up to thousands of dashboards that you have to manage. But what you can see here is if I just go ahead, instead of selecting this line, I go ahead and select this line right over here, what you can see is all the dashboards along the top are the same. They look identical. And what we're doing is we have a small connectivity model underneath the hood, which basically says, hey, this is the particular asset, and these are the measurements that are associated with that asset. And so the software automatically basically swaps out on this dashboard the signals for this particular asset compared to the asset that I was just looking at. So there is that capability where we have template creation. In terms of out of the box, the dashboards, they are not pre-configured, but in the utilities that we've worked with, we've always been able to help set up some of them or copy dashboards from other systems and bring those into the system. So we can help out with that. But just to show you just kind of how simple it is, I'll go ahead here. Just, you can create a dashboard here. Just directly from the user interface. You can do it while you have the system live. And then you can just click add panel. You can drag and drop these panels to wherever you'd like. So I can drag it up here. And then I have a whole list of different panel types that are available for you, again, to design. Here, I'll just select the time series trend. It's going to give you a nice little message that says it hasn't been fully configured yet. And you can come in here and you can just choose the type of data you'd like. So let's look at line-to-line voltage magnitude. And I want to look at line-to-line voltage magnitude. I'm just going to choose some random locations here, but across a bunch of different locations, and click apply. And that quickly you're looking at data and configured it. And so yeah, we can put that in as well. One of the things I'll note too, just as a note here, while I have y'all, is that when you create a dashboard, you'll notice there's a little user icon here, and that's letting you know that that dashboard is private to you. But you'll see all the other dashboards have been published. And so you can actually, after you're done configuring a dashboard, you can come in here and you can publish this dashboard. And now this dashboard is now available to all the other users that are on the system. And so that's a really nice way to be able to have your own location where you can do some stuff, but then also make sure information is shared across your organization without each individual user having to create their own set of dashboards.
Okay, I got one here that I'll answer quickly, Jared. The question is, would it make sense to include another VT in that station at the same voltage for comparison purposes and include that in the analysis? So this is back to the instrument transformer failure. And yeah, that's a great thought. I think it's more appropriate for that to be done just at the substation level because those measurements are right there. And in fact, the SEL RTAC is working on a solution that does that, and also sort of takes in bus configuration and stuff to make it work really well. Okay, Jared, here's one for you. What are the communication bandwidth requirements from a remote station?
Yeah, that's a good question. So utilities have transmitted this data over serial connections, so it's not super significant or as significant as it might look. SEL does have a spreadsheet that we can share with you that gives you a little bit of the bandwidth requirements. You can, of course, it's dependent upon the number of signals you choose, the number of locations within a substation. So it does vary quite a bit, but there's a spreadsheet that we can help walk you through in terms of sizing your system and making sure your communication's right. And that maybe kind of leads me on to the next, a next question, maybe a follow-up that I didn't really talk about. And that's like, what would be the next step if I wanted to learn more? And potentially, you can always reach out to Synchrowave at sellinc.com or anywhere, or just our traditional field application engineers, and they can point you in the right direction by reaching out to them. But one of the things for utilities that's looking at this, investigating whether this is the right solution or an industrial site, would be really to reach out to our team. What we'd love to do is work with you, understand a little bit more of your requirements or some of the applications that you're interested in. And then what we look at is an evaluation or a demonstration period or a trial appropriate for your kind of environment? Does that make sense? And then go from there. So that's just a couple of the next steps that we might want to pursue if this webinar was intriguing.
Okay, we've got another question here, Jared. How do you decide the PMU locations? How many PMUs are needed in a single substation? Whether one for each generation, feeders, etc.
Yeah, I love that question. So that's a good one. So I'd say there's kind of 3 tiers that we have. The first tier that I would recommend is that you install a PMU to at least monitor the bus voltages at each of your points of interconnection. So if you have a substation that's at a point of interconnection, whether or not if you're a microgrid installation, you want to measure that interconnection, or if you're a utility and you're interconnecting with neighbors, definitely want to have your interconnection points monitored. The second point I would recommend is I'd recommend installing, and in these cases, I'd recommend both voltage and current as a minimum, but installing them at any location where you have large generation sources, or if you have large distributed, large DER sources as well, like solar farms, wind farms. We're seeing a lot of dynamics based on those, and as an industry, we just have so much to learn in terms of from that area, and I think having this data is going to provide you a lot of value from those specific sites. Lastly, in terms of the basic requirements and locations, I'd recommend is if you do have transmission lines that are high capacity lines that are critical, then I'd recommend installing, again, voltage and current measurements there. After that initial set, and again, you can work slowly to that. Okay, the system can be deployed with just a couple of locations, and then you can work up. But after that, typically utilities work on getting complete coverage of their high voltage system. So whether it's 230, 115, 345, 500 kV, and in general, the step after that is getting measurements for each transmission line and the bus in those locations. We've just seen over and over time again, having the current measurements for the lines and those three-phase bus measurements are just become very valuable to utility partners we've worked with. And the last item, I know I'm going on here, but if you can, and if you're just deploying a new system, when you do deploy, please wire in the circuit breaker statuses as well along the line. A lot of the utilities we've worked with have gone back out to the field and wired those in, just because if you do the method traditionally where you would connect back into your SCADA system, which can be done, the time synchronization is between the breaker status changes and the measurements just doesn't quite line up with the timestamps that the SCADA puts on those breaker status. So just something to be looking at and keep in mind as you go forward and make a plan to deploy and roll out. So I think with that, we probably should wrap up. We're at an hour. It's been a fun time. We'll respond to the rest of the questions. Thank you so much for your participation, everyone. Tristan, did you want to wrap up?
Yep. Thanks, Jared, and thanks, Josh. And thanks, everyone, for attending. As Jared said, we're at the end of the webinar, but if your question wasn't answered during the presentation or the live Q&A, we'll follow up with you via email afterwards. And if you'd like to learn more about this topic, you can visit our websites and also inquire about a live demonstration there if you'd like to request one. So we hope everyone enjoyed today's event, and we look forward to seeing you all in future SEL webinars. Thank you very much.